Okay, welcome back. So as you can see, or as you can guess, I'm recording these back to back. I want to avoid coming here as much as possible. Right now we're going to talk about convergence of series. In particular, integral test of series. So let me briefly recall. If we have a sequence of numbers A0, A1, A2, A3, etc., then we can define the partial sum of this sequence to be this finite sum. So the sum from I goes 0 to n of AI. Now, if the limit of the partial sums Sn exists and let's say is equal to S, then we say that the infinite sum, the sum from I goes 0 to infinity of AI, converges and is equal to S. If this limit, on the other hand, does not exist, then we say that the infinite sum diverges. So basically, if we have an infinite sum, there are two basic questions you could ask. One is, does the series converge? And two is, if the series does converge, what does it converge to? Now the second question, what does it converge to, is very difficult in general. One of the exceptions is, as we saw in the previous lecture, geometric series. This is one of the types of series where you could actually easily evaluate the infinite sum, but in general it's very hard. But the first question, does it converge? Could still be hard, but it is often much easier than actually determining the sum. So, question. Question. Given an infinite sum, does it converge? Now, the most basic test is, I think, what they call the Nth Term Test, though I'm not sure if this language is used in the book, but definitely it's written on page 490. So, if this sum, the infinite sum, converges, then the limit of the AIs as I goes to infinity is equal to 0. So if this converges, this is 0. Now conversely, what this means is that if this limit is not 0, so this implies that if this limit is not 0, then the infinite sum diverges. Okay, so you may want to pause now and think about how these implications are related. So let me do an example. So this is an example from the book. Question, does this converge? Now, if we look here, we see that what we should do first is compute the limit of the AI. So in this example, this is AI. So the limit as I goes to infinity of AI in this example is equal to 1, right? Because e to the minus I goes to 0 as I goes to infinity, so this goes to 1. And of course, 1 is not equal to 0, as everyone knows. Therefore, this series does not converge, it diverges. Okay, so this is one of the most basic tests for convergence. Probably is the most basic one. If you see an infinite series, the first thing you should think about probably is, does the limit of the numbers in the sequence go to 0 or not? Okay. Now let me just give a caveat. The converse isn't true. If this is 0, it does not mean that this converges. So, example, the harmonic series. So this is a famous series. So here, I'm going to start the series from 1. It doesn't matter where we started from. It's, whether or not we start from 1, 0, whatever. Well, here we can start from 0. Well, this isn't defined as 0, which is why I'm starting from 1, but this doesn't, cause any issues with the theorems. So this is called the harmonic series. And this, as you can see, the AI here is equal to 1 over I. So the limit as I goes to infinity of AI, it does go to 0. So this limit is 0, right? 1 over I goes to 0 as I goes to infinity. However, the harmonic series diverges. Okay, so this is important to understand. If this converges, then this is 0. But if this is 0, it does not mean that this converges. So make sure you understand this, and this is a good example to know. Now, on page 490 of the textbook, there are all these nice properties that are written about convergence properties of series. So I'm not going to write them all down, but basically, well, one of them I just talked about, which is this one. Some of the others say basically what you intuitively maybe would expect would be true for a series. That if two series converge, then their sum converges. If a series converges, you can multiply by any real number, and that series will also converge. So, like, if these two series converge, sorry for the bad writing, then the sum, so then this series converges, and this series, this series converges to this plus this. So that's this is a linearity property of series. So that's important to know. Again, it's in page 490 of your book, so you should look at that. Another one that's important to understand is that if you have a series you could change finitely many of the terms, and it won't affect whether or not it converges or diverges. So this is basically because you can always, finite sums always converge. So if you have an infinite series and you change only finitely many of the terms, so you have an infinite series AI. So we have, A0, A1, A2, A3, etc. If we change finitely many of the values, it'll converge if and only if the original series converges. So changing finitely many values has no effect on convergence. It will, of course, change what the sum is, right? It definitely changes what it converges to, but it won't change the fact that it converges. So another test for convergence is called the integral test. Okay, so it's important to state this exactly. So the integral test says that if an is equal to fn, where f of x is a positive and decreasing function, then, so I'm going to move to this side of the board. Then, this series converges if and only if, so I'll use the equivalence arrows, this integral converges. So, example is the harmonic series. Okay, again, we could change the initial point, it doesn't matter. So I could use any number here. I could use a 1, a 2, whatever. So, and this equivalence will still hold. So let me look at this integral. So this integral diverges, right? You could use the fundamental theorem of calculus. This is like, it's like this, basically. And log of x goes to infinity as x goes to infinity. So this diverges. Therefore, okay, I'll move to this side now. I actually get better at this Blackboard organization. Therefore, the harmonic series also diverges. So the reason is, here our f of x is 1 over x, so 1 over n is equal to f of n. So let me just write this. F of x, where should I put this? Totally confusing. So f of x is equal to 1 over x. Hopefully you can see that. So this function is decreasing and it's positive. And a sub n is equal to f of n. Therefore, we could use the integral test, which says that this converges if and only if this converges. This does not converge, therefore this also does not converge. So that's probably the simplest example of using the integral test to show that a series diverges. Okay, so now what else? Maybe I should. There's a nice picture in the textbook. I'll try to. Maybe I'll just draw it out. The idea behind the explanation behind the integral test is, it's like how you could approximate the area under a curve by a Riemann sum, which is a finite sum. It's the same idea, basically. I'll I'll do one direction. So let me draw a picture of some, suppose this is some function f of x. So y, whatever. So this function is decreasing and is positive. So what's the idea behind the integral test? So let's say this is 1, 2, 3, 4, etc. Let's look at the right-hand Riemann sum. So here, let me fix this. It looks like it diverges now. So let me put it there. So let's look at the right-hand Riemann sum. So let's draw the rectangles. So we have this rectangle. So this would be like f of 1. And the next rectangle is this. Next rectangle is this. So this point right here is equal to f of 1. This point right here is equal to f of 2. This, the value here is equal to f of 3. And you can keep going. So the point is that, I'm going to erase this now. The point is that the integral here is bigger than the sum. So if we add up the areas of all these rectangles, so these things all have length 1, and the height is f of this point. So if we add up the areas of all those rectangles, we get this, right? Now this from the picture, so it's clear that, well, hopefully you can see from the picture that the area under the curve is bigger than the area of all these rectangles. So this is less than or equal to the integral of f of x from 1 to infinity. Okay, so what does this tell us? So let me just remind you of a theorem from chapter 9.1. It's called the bounded convergence theorem. So bounded convergence theorem. If you have a sequence of numbers which are monotone and bounded, then the limit exists. E1, E2, E3, etc. is bounded and monotone. Then the limit exists. So, I think this is going to be hard to read. Need a bigger piece of chalk. Hold on. Okay. So if we have a sequence of numbers, they're bounded, they're monotone, the limit exists. So now, if we look here, if we look at the partial sums, because f is a positive function, the partial sums are monotone increasing, right? F is positive, so the partial sums are increasing. And if this limit exists, if this exists, if this converges, then the partial sums are bounded by this integral. Therefore, if f is positive decreasing and this integral converges, then this sum also converges. Maybe the picture is more clear. You should maybe you can understand it intuitively from the picture, but this is what I was getting here is more of mathematical explanation, but definitely, at the very least, you should know the integral test, what it states exactly, how to use it in some examples. So here I was trying to give an explanation for why if the integral converges and so does the sum, but you could also give a similar explanation for the other direction, which is if this converges, then so does the integral. Yeah, so let me think. Maybe I'll leave it there. Right, so you should think about an example you should think about is this sum. Let's go n equals 1 to infinity of 1 over n to the p. You should use the integral test to determine for which p values this converges. Okay, and I'm just going to leave it there. Thank you for watching. Again, see you next time.